Jefferson Lab, scientists can advance our understanding of matter itself by probing quarks and gluons in the atom's nucleus with beams of electrons from the superconducting accelerator. Jefferson Lab has an educational mission as well. The Jefferson Lab Science Series features scientists and engineers who are gifted in making their work not only informative but fun. The Science Series is held once a month in the Jefferson Lab Auditorium. The presentation is live, spontaneous, and unrehearsed.
All right, greetings, folks. I'd like to welcome you to the Jefferson Laboratories Science Series. And before we get started, a few introductions and announcement of the next talk. I'm Dr. Michelle Shin. I am a physicist in the Free Electron Laser Department, Accelerator Division here at Jefferson Laboratories. And I've been here now for a few years, and you've probably seen me on the public channel giving talks on different things. And I'm really happy to, in a few minutes, announce our speaker for tonight. Before I do that, I'd like to say a few words about and announce our next science series. It'll be given on Tuesday, November 18th, right here in our Jefferson Laboratories Auditorium at 7. The talk will be Adventures in Science. It'll be given by Professor Thea Keppel at Hampton University, and I think a couple of her graduate students. And I'd like to invite you to that. Thea's really a neat person, and I think you'll really enjoy what she has to show. I'd like now to announce our speaker and give a few introductions. Dick Berg. Dick attended high school in a suburb in Chicago, and had a great interest, it appears, in both music and science, which I can relate to. And he actually attended a liberal arts college, Manchester College in North Manchester, Indiana, and originally planning on being a music major, but found that he really enjoyed physics and chemistry, so he took all the science he could. And he decided on graduation, instead of going into music, he decided to go into physics. And in graduate school, he worked on cyclotrons and learned a great deal about them. And then he joined the faculty at the University of Maryland in College Park, and then he became, I guess, the head of the demonstration lecture stuff that they do there. And he's maintained his interest in music and the physics of music. He's actually an avid musician in early music himself. And he's published a textbook. I want to get the authors right. The textbook is entitled The Physics of Sound by Richard Berg and David Stork. It's published by Prentice Hall. I highly recommend it. And so without further ado, I'm going to introduce Dick Berg. Thank you.
Thank you. Welcome to the physics program. Now, the program for this evening is going to be the physics IQ test. I know as soon as I said that, some of you got a funny look on your face because you hadn't studied. And I know what your first question is going to be. So let me tell you a little bit about the physics IQ test. I have a collection of gizmos and doodads up here, all little physics experiments. Each one, I will first of all bring it up and tell you a little bit about it, maybe how it works, and then suggest an experiment which we can do with that apparatus. Now, I won't do the experiment, but the possibilities, the possible results of the experiment will be pretty clear. 1 or 2 or 3 or 4 different possibilities. We'll go through and I will enumerate those for you just to clarify things. And at that point, then, you get a chance to vote on what you think the outcome will be. Now, you have to vote. See, I don't know is not a correct answer. All right? Now, what makes this set of experiments perhaps a little more interesting is that they have some counterintuitive aspect to it, or some little, I don't want to say trick, because it really isn't a trick, it's just possible to view it in a number of different ways. In fact, I've done this program for a large number of groups, all the way from middle school kids, high school kids, physics students in college, graduate students, and physics professors in professional meetings of the American Association of Physics Teachers. And I found that if they haven't seen these things before, they all get about the same score, which is an interesting phenomenon. So, what we're going to do is sort of go through these. We'll do them a little faster than we usually would do if we worked on them, did them in a physics class. And we'll see how your physics IQ develops. Let's put this down here so it won't be in the way of the TV. We'll start with a simple one. Have a super ball here. In fact, any ball can do. Doesn't even have to be a ball. And I'm going to hold it up here and then release it from rest. That means drop it. Physicists have to have terms that nobody else understands, so that you have to take physics class, right? All right, so I'm going to hold this ball up and release it from rest. And the question is, when I do that, what will it do? Will it go up, will it go down, or will it stay where it is? Okay, I guess you're ready to vote. Who says, when I hold this ball up like this and release it from rest, that it'll go up? Raise your hand. A few suckers, a few. How about down? Raise your hand. Good. How about it'll stay where it is? All right. A few skeptics. All right. Well, let's see. Of course, it goes down. In fact, that's sort of the definition of down, isn't it? Toward the center of the earth, isn't it? Well, almost, except for the fact that the earth is oblate and is spinning. It goes toward the center of the earth, so almost. All right, well, that was a pretty good one, and most of you got that pretty well. Here's a more complicated dropping question. I've got a book and a piece of paper, good book, Physics of Sound by Berg and Stork. I'm going to hold them up at the same height and release them from rest simultaneously. Which one will get to the table first? The book, the paper, at the same time? Well, I guess everybody's ready again. Let's go ahead and vote. Who says book is first? Good. Who says paper is first? Boy, never learn, do they? All right. How about same time? Okay. I guess some of you didn't like that. Let's do it again here. Well, maybe what you were thinking of is more like this, huh? All right. Tell you what, we'll grade easy here at the beginning. Give yourself credit for either saying that the book gets there first or the same time. All right. That's fine. Here's another more complicated dropping experiment. I've got a weight, it's a 50-gram steel weight, hanging on a spring from the underneath side of this plastic beaker. This works real well with styrofoam cups, too, if you want to make one yourself, a rubber band and a styrofoam cup. Now, you can see the weight there. What I'm going to do is to hold this up and, again, release it from rest. Now, you remember from the first question that it'll go down, right? But the real question is this. When I release it from rest and the whole thing starts to fall down, what will the weight do? I can think of three possibilities. It might extend a little bit, sort of like a parachute effect. It might go up into the cup, or if you can't think of any reason why either of those two things would happen, it might just fall in the same orientation with the weight about in the same position that it is as I'm holding it. So the question is, when this cup falls, what will the weight do? Will it extend? Will it go up into the cup, or will it fall in this orientation? All right, well, there seems to be a little more disagreement, so maybe we ought to go ahead and vote. It's the only way you decide these things in a democracy, isn't it? All right, who says, when I release this cup from rest and it starts to fall, that the weight will extend a little bit? Good. How about the weight will go up into the cup? More. How about the weight will just stay like this? All right, good. It's pretty close to a statistical distribution. Let's do it. Ready? Go. What did it do? It went up into the cup, didn't it? This phenomenon is known as weightlessness in free fall, or if you want to be real technical about it, sometimes it's called apparent weightlessness in free fall. Of course, these things aren't really weightless because their weight is what's pulling them downward. However, in the frame of reference of the cup and the weight, anything falling together becomes weightless in that frame of reference. What is it that keeps the spring extended? It's the weight, isn't it? So when they begin to fall and everything becomes weightless, there's no weight, therefore there's no force on the spring pulls the weight back into the cup. In fact, this is the reason why astronauts appear weightless in space capsules encircling the Earth. They're only about 200 miles maximum above the surface of the Earth, and that's only a couple of % of the diameter of the Earth. So that the acceleration of gravity, the force of gravity on them up there is about the same as it is on Earth. The only reason why they appear to be weightless and why things stay out in space is because while they're moving through the Earth, or through space, parallel to the surface of the Earth, the effect of that is that they are falling toward the center of the Earth. So they're actually in free fall. And so the entire space capsule and everything in it is in free fall and therefore weightless, or apparent, in a state of apparent weightlessness. And that's why it seems to have the effect of weightlessness. All right, here's another falling experiment. This device is a funnel cart because it's got a funnel on it. It's spring-loaded. If I release the spring with a ball in there, the ball goes straight up, falls back down into the cart. I can roll this cart along the track. When it gets to a certain point, the spring will release and push the funnel up. Here's the question. With the ball in there, now I'm going to push it along. When it gets to this point, it will eject the ball perpendicular to the track. Where will it fall? In front, behind, or in the funnel? This one's a little harder, I guess. All right, let's go ahead and vote. Who says, when I push the cart along and the ball ejects, that it will fall in front of the funnel? Raise your hand high. Good, no guts, no glory. How about behind? Good many there. How about in the cart? Good, it's about even between behind and in the cart. You ready? Of course, it falls in. This demonstration illustrates the idea of separation of components of motion. As the cart is coming along, the entire thing, the ball and the cart and the funnel and everything is going that direction. The ball gets ejected vertically with respect to the cart frame of reference, but it's also moving along horizontally. So if I do it again, you'll notice that at all times the ball stays directly above the funnel as it goes up and then comes back down, and of course it lands in the cart. This is actually the reason why we can throw a ball up in the air and have it come down on the surface of the Earth into our hands, isn't it? After all, the Earth's surface is moving at, what, 1,000 miles an hour or so, isn't it? And if this didn't work, then when you threw a ball in the air, it would come down some distance back, well, in the opposite direction from the direction which the Earth is moving. All right, well, let's do another variation of this experiment. I've got a weight, about a 200-gram weight here, over a pulley, and I'm going to attach it to the funnel cart. And we'll again load the spring. Now when I let it go, again it will eject right here. And the question is, where will it fall? In front, behind, or in the funnel? All right, let's go ahead and vote. I think from the sounds of it, appears like everybody's ready to vote. All right, who says in this circumstance the ball will fall in front? Raise your hand. None. All right, that's pretty good. That's a learning curve, isn't it? All right, how about behind? Raise your hand. Good many there. Good. How about in? All right. Of course, it falls behind now. The reason for this is that the cart is now accelerating, isn't it? It's getting faster and faster because of the force put on by the weight over the pulley. And so if the cart gets faster and faster, when it ejects, the ball doesn't get any faster after it ejects, but the cart does, so the cart outdistances the ball, doesn't it? Watch again. Now, there's more than one way to accelerate this cart along the track, isn't there? For example, I can do it like that. Now, when I let the cart go, it will accelerate down the incline. And again, the ball will eject when it gets to the same point. Where will it land? In front, behind, or in the funnel? Seems to be a distinct difference of opinion here. Maybe we better go ahead and vote. Well, let's see. Argue about it for about 20 seconds. Convince your neighbor. Okay, that's enough. We don't want to get it right. Oh. All right, let's go ahead and vote. Who says, as the cart accelerates down the incline, the ball will land in front of the funnel? Raise your hand. Raise it hand. Good, good, high, good. Of course, it's got a leg up, doesn't it? Because it's tilted, so it's going an angle. All right, how about the ball will land behind the funnel? Yeah, that's good because, of course, the cart is accelerating down the incline, so it'll get ahead, won't it? How about in? Who says in? Now, you all aren't voting. Let's try this again. Nah. Who says in front? How about behind? And in? Okay, you ready? Of course, it's easy to see that the cart accelerates down the incline. What's a little more difficult to see is that so does the ball. The reason why is that gravity is tilted with respect to the incline, isn't it? It's at an angle. So there's a component of the gravitational force perpendicular to the incline, which pulls the ball back down, and a component parallel, which in fact gives both the cart and the ball an acceleration down the incline. So if you tilt your head so that this appears horizontal and vertical is at an angle, then you'll notice that just like the first time, the ball will stay directly above the funnel at all times. Let's try it. Everybody tilt your head. Ready with the cameras? Yeah, that's it. Let's see, let's do a variation on this. Suppose I push it up. It'll eject right here. Same way. Will it fall in the cup? Whoop. I guess there are two answers. Yes, of course it'll fall in the cup, and no, of course it won't fall in the cup. All right, who says yes, of course it'll fall in the cup? Not very many. Who says no, of course it won't fall in the cup? Yes, of course it'll fall in the cup. It's actually the same equations. The only difference is you put a minus sign in front of the acceleration. For those of you who are in high school physics, try it. Interesting experiment. All right, good. Here I have a meter stick. It's actually a yardstick on the other side, but that doesn't matter. I can hold my meter stick up. One end I'm holding at the very end, supporting on my finger. And the other end I'm supporting about a quarter of the way from the opposite end on my finger like this. Now what I'm going to do is to move my hands together, just like that, until they meet. And the question is, what will happen? Will it fall off this side? Will it fall off this side? Or just to be complete, let's say neither. I'm going to move both hands together, same rate, just like this. All right. Let's vote. Who says, when I move my hands together, that the meter stick will fall off this way? Raise your hand. Good. That's a lot. Good. How about the meter stick will fall off this way? Raise your hand. Good. How about neither? Pretty close to statistical there. All right, you ready? Let's do it. In fact, what happens here is that the hand which is closer to the center supports more weight, doesn't it? And therefore it has more frictional force. So the other hand slides until it gets closer to the center, and it goes back and forth and always ends up at the center of mass of the system then. In fact, that's a definition of the center of mass, that it supports an object. You can support an object from a single point at the center of mass. Well, I'm curious about this meter stick because I'm supporting it at the 53 centimeter mark. Let's see. Suppose I put 100-gram weight on the end. And I'll do the same experiment. Now what's going to happen? Raise your hand if you think the weight side will fall. How about the other side? And how about neither? Okay, you'll have to do that at home. Okay, good. Well, let's see. You can come up and play with that later if you didn't believe it. Okay. Here we have a simple system. Got a fixed support point up at the top there. We've got a thread holding a weight here, a second identical thread holding a second identical weight, a third identical thread with a little aluminum bar down here that I can pull on. And the question is, when I pull down here, which of the threads will break? Which thread will break? The top, the middle, or the bottom? Well, I hear a difference of opinion. Let's go ahead and vote. Who says, when I pull on the weight on the bar down here, that the top thread will break? Raise your hand. High. Good. How about the middle thread will break? Raise your hand. Good. How about the bottom thread will break? All right, looks like the top thread has it. Are you ready? What's the important physics idea here? I think it's inertia, isn't it? When I yank it, the bottom rod has a certain amount of inertia. It's moving. This weight has a certain amount of inertia due to its rest, being at rest, and therefore when the thread is extended all the way, is tight, it develops very quickly a large amount of tension, doesn't it? And it breaks. Now, let's do the experiment again. If I do it now and pull slowly, what's going to happen? Well, let's see. When I pull slowly, I create a certain amount of tension in this thread. This weight adds to that tension in this thread, doesn't it? And this weight adds more to the tension in this thread. So as I pull, the tension in the top thread will always be the greatest, won't it? So if I pull more and more, the top thread breaks. Because in this case, it's the addition of a series of forces, isn't it? Okay, good. Of course, a physics experiment or physics program has to have pulleys and scales and stuff in it. So I brought this experiment for you. See, here we have a couple of identical spring scales. If I pull on this, you see I can exert a force on it. Here, a little frame with a spring scale hanging from the top, and on the bottom is a little pulley. What I can do here, I've got a weight, I've got a rope attached to the bottom of the scale of the frame going over the pulley, and so now if I pull on the free end of the rope, I can exert a force on the scale. If I hang this entire system on the upper scale, we can see that this part weighs about 5 newtons, right? That's the gravitational force with which it is pulling down there. Now, here's the question for you. I'm going to come down here to the pulley, and I'm going to pull this very gently until it goes up to 10 newtons. What will this one read when I pull this down so that it reads, this bottom one reads 10 newtons? What will the top one read when I pull enough on here to make the bottom one go to 10 newtons? 3 possible answers. It'll stay where it is at 5 newtons, it'll go to 10 newtons, or it'll go to 15 newtons. It might stay where it is because I'm pulling down, but after all it is pulling back up. You may not like that argument. You may say, well, if I pull down here so this reads 10, maybe this 5 plus 10 has to be 15. So what will the top scale read when the bottom scale goes to 10 newtons? 5, 10, or 15? All right, let's vote. Who says when the bottom scale reads 10 newtons, the top one will remain at 5? Raise your hand. Good. How about it'll go to 10? Raise your hand. A few there, a few more. How about 15? Good. You ready? Goes to 10. Why does it do that? Well, let's see. What I'm actually doing is pulling with a force of 5 newtons. There's 5 newtons of tension in both of these threads, ropes. Therefore, I'm pulling down on this lower spring scale with a force of 10 newtons. But there is 5 newton force pulling back up on the bottom of the frame, so it actually only adds 5 newtons to the top scale, which means that it's 5 plus the 5 that I've added, or 10. Okay. All right, well, most of you are doing pretty well so far. Here's an unlikely looking contraption. This device moves like this, and it'll stay wherever you put it. Here's the experiment. I've got 2 identical 100-gram weights. I'm going to put one out at the end here and one in toward the center. Now I'm holding it. The question is, what will happen when I let it go? Will the right side go down? Will the left side go down, or will it stay in balance? Okay, let's vote. Who says, when I let this go, the right side will go down? Raise your hand. Good. How about the left side will go down? There's a few who are trying to psych me. How about it'll stay where it is? A few there? If that's correct. In fact, it'll stay wherever you put it. Why does it do this? What's the idea in physics? I think it is that no matter how you operate this, the position, the vertical position of the center of mass doesn't change, does it? One half goes down and the other half goes up, or vice versa, by the same amount. Therefore, because the center of mass doesn't change position, this is in what is called neutral equilibrium, isn't it? So it will stay wherever you put it. If you put an extra weight on one side, like there, now what will happen? That side goes down. How about if I put the extra weight over here? That side goes down. How many of you have worked with a device like this? Raise your hand. Actually, this is the mechanism in a pan balance. The pan balance is sort of like a Scotsman's kilt, because nobody ever looks up under there to see what's really there. Now, if you do, you'll see, in fact, a mechanism which is similar to this device, which is called a Roberval balance. Here's a comparison between the Roberval balance, this arm balance, and a pan balance. Notice that there are two main differences between them. The first difference is that we put the weights out in these arms. The little circles here are places where the thing can move, right? Rotating joints. We put the weights out on the arms to purposely confuse you, make you think it was going to be like a teeter-totter, didn't it? The second primary difference between these two, of course, on a pan balance, it's the pan is rigidly attached to the vertical beam, the vertical part there. The second major difference is, notice that the top beam is straight on our Roberval balance, but it's got sloped shoulders on the pan balance. Now, for those of you who are into trig a little bit, you may recognize now that if you put the same weight on each pan, when you move the pans from their equilibrium position, whichever pan, because of the slope here, whichever pan moves up will move further up than the one opposite it moves down. Due to trigonometry, isn't it? Due to the angles here, right? This rotates up, and it's almost vertical. This one's starting to rotate around in a circle. And so that means that the neutral equilibrium of this pan balance, this Roberval balance, is replaced by a stable equilibrium where the two pans are horizontal. The top beam is horizontal if the same weight is placed on each pan. What this is a torque balance, isn't it? That is to say, it eliminates the problem that you get by placement of the weight on either of the pans. So you can put the weight anywhere you want on the pan, and this removes the torque. Right? Of course, that's what you want, isn't it? This kind of a balance is used in the grocery store when you go, you know, and the cashier puts your bananas on the big pan. You know, the laser sticks up through the pan to measure or to do the scanning. You don't want the weight of your bananas to depend on where you put them on the pan, do you? And so this type of device, actually in the pan balances or the beam balances that they use at the grocery store, it's 2 or 3 of these in this direction as well as this mechanism. So the idea is this is a torque balance, a device which a device which corrects for torques and allows you to put the weights anywhere on the pan without affecting the balance. Okay, good. As long as we got our pan balance out, let's do a little experiment with this. I've got a beaker of water and a couple of weights here, and they should be approximately in balance. Oops, here we go. Put a little bit more water in here, I guess. There we go. Is that pretty good? Well, too much. Shucks. There we go. That's pretty good. Now, here's the question. Suppose that I go up and stick my finger into the water. What will the balance do? Will the water side go down? Will the weight side go down? Or will it stay in balance? On the face of it, that's a silly question, isn't it? You can't put force on water by sticking your finger into it. Well, let's go ahead and vote. I think everybody is pretty much agreed. Who says, when I put my finger in this, the water side will go down? A few, good. How about the weight side will go down? Raise your hand. How about it'll stay balanced? Okay, there's 95%. You ready? So now we got to explain that. We got a dumb result. Let's see. When you sit on the side of a swimming pool and let your legs dangle into the water, do you feel any force on your legs? Yes? You feel a buoyant force, don't you? They bob up because of the buoyant force of the water on your legs, don't you? How many of you have ever felt that? Raise your hand. Okay, good many. All right. Next time you're in a swimming pool, notice that. May have to wait till next June. But so let's see. According to the laws of motion, when I put my finger into the water exerts a buoyant force on my finger. Therefore, according to Newton's third law of motion, my finger has to exert a reaction force on the water. And that's the force which causes that pan to go down. You believe that? I think so. Action, reaction, it really works. Okay. Here's a question that I remember arguing about when I was in middle school or junior high school, they called it in those days. Suppose you're out in a rowboat, and your rowboat, you're on a closed lake, closed pond, so no water can flow in or out of the pond. And you have a big rock in your rowboat, and you take the rock and throw it over into the lake, into the pond. What will happen to the water level in the pond when you throw the rock over and it sinks to the bottom? Here's our model right here. We have our boat, plastic boat with a rock in there. The rock is a lead weight, and the water level in the pond is up to the top of the black tape here. So what's going to happen when I take my rock, my lead weight out, and let it sink to the bottom of the pond? Will the water level in the pond go up, go down, or stay the same? This is a little more complicated. All right, let's vote. Here we go. Who says? Raise your hand if you think when I let the rock out of the boat into this pond and sinks, who says the water level will go up? Raise your hand. Good. How about the water level will go down? Good. How about it'll stay the same? Okay, it looks like it's at least about 60% same and about equal amounts up and down. Are you ready? What happened? The water level went down, didn't it? Now the question is why? I think this is a problem that middle school kids have all studied, but they don't study it right. Whenever I go to a middle school and show them this experiment and then ask them to tell me the laws of buoyancy, they almost all can. Let's see. What's the first law of buoyancy? Something that floats displaces its weight in water. How many of you have heard of that? Raise your hand. All right. And the second law of buoyancy, something that sinks displaces its volume in water. How many of you have heard of that? Boy, well, a good many. The thing that they don't teach you is what displacement means. Let's see. Displacement means when I push down on the boat, and the boat pushes into the water, it displaces more water. The more water is displaced, the higher the water level in the pond, right? Does that demonstrate that effect? I think so. If the weight is in the pond, it's in the boat, it's floating, isn't it? So it displaces its weight in water. That's a lot of water, isn't it? Because it's lead. If the rock sinks, it displaces its volume in water, which is a lot less water, so the water level in the pond goes down. A variation on this is what happens when a boat out in the middle of the ocean sinks. Does the water level in the ocean go up, go down, or stay the same? Well, it's by a small amount, of course. But okay. All right, well, we're doing pretty well here. Which is faster, rolling or sliding? Well, there's a difference of opinion. Let's do an experiment and see if we can figure it out. Here I have two almost identical aluminum cylinders. This one, if I put on its edge, it'll roll down the incline. This one has 4 tiny little ball bearings on it, so if I put it on its end, it slides without friction down the incline. So the question is, which is faster? Rolling or sliding or the same? When I start the two up here, which will get to the bottom first? Rolling, sliding, or the same? Which is faster, rolling or sliding? Okay, let's vote. Who says rolling is faster? Raise your hand high. Good. Who says sliding is faster? Raise your hand. Good. How about same? Raise your hand. Good. About equal, right? Close. Ready? Let's do this again. I'm not sure anybody believed it. Yep. Sliding is faster than rolling. Now we got to explain that. The reason has to do with conservation of energy. Why does anything go down the incline? Because its potential energy, its gravitational potential energy, is being converted into kinetic energy, isn't it? Energy of motion. In the sliding object, all of its potential energy is converted into translational kinetic energy. That is to say, it's all moving along at the same speed, isn't it? Every point on the sliding object. With the rolling object, we get two kinds of kinetic energy. We get translational, because it's all moving along, and we also get rotational kinetic energy. So in the case of a rolling object, its initial potential energy is divided into two parts, separated: translational and rotational kinetic energy. So because some of the energy goes into rotating the thing, that means there isn't as much left for pure translation, and therefore it rolls more slowly than the sliding object. Sliding is faster than rolling due to conservation of energy. Of course, this is sliding without friction. If you have friction, then it's very, very easy to get the opposite occurrence. Here's an important piece of physics apparatus. Let's see. This tricycle has been fixed. That is to say, the front wheel doesn't turn, and it can only move forward or backward. So if I tie a rope to the pedal here, hold the rope parallel to the ground and pull very gently with the pedal pointing upward, I can pull the bicycle toward me. Here's the question. I put the pedal down, hold the rope parallel to the ground, and pull very gently the same way. What will the tricycle do? Will it come towards me? Will it go away from me? Or will it stay in place and the wheels spin? All right. Let's vote. Who says with the wheel down and the rope parallel, if I pull very gently now, that the tricycle will come towards me? Raise your hand. A few, good. How about the tricycle will go away from me? More. How about it'll stay in place and the wheels spin? Good many there too. Forward loses. Forward is right. Now, let's analyze this. It turns out that this has a lot to do with just with the way you look at the thing. If I put my key here underneath the pedal, notice that even though the pedal appears to be going in the wrong direction in the frame of reference of the wheel, it's still coming towards me, isn't it? That's an interesting concept. If you had one of these gizmos, a little loop thing on your pedal, and you wanted to start with your foot in this position, you wanted to start your tricycle going forward, how would you do it? You'd pull backwards, wouldn't you? You want to make the wheel go around like this, because that's what makes your tricycle go forward. Turns out there's a little more complicated than that. If you, we've made a little pedal extender, which I don't have time to put on right now. If you extend it on down, if you pull with a radius less than the radius of the wheel, it'll come forward. If you pull with a radius greater than the wheel, it'll go backwards. And if you pull with a radius equal to the radius of the wheel, it'll stay in place and the wheel will spin. So, all right. Here's one of my favorite experiments, this gizmo. We've got two tracks, two identical pool balls. Well, they're almost identical. You can't see any difference, can you? No. And what we're going to do is to launch the two balls from this end with the same speed. And the question is, who will win the race? Which one will get to the other end first? The ball with a straight track, the ball with a dip track, or will it be a tie? All right. Let's vote. Who says the straight track will win? Raise your hand. Good logic there. After all, the straight line is the shortest distance between 2 points. Who says the dip track will win? Good. Good logic. After all, it is going to go faster when it's down in the valley there. Who says same time? Overwhelming majority. Of course, when it goes back up, it'll slow down, and that means that they'll sort of cancel each other, so they should get there at the same time. Let me do something here. We'll just sort of play physics teacher here. I'm going to tell you exactly how this works, and I want then anybody, after I get done, anybody who believes me and was willing to change their mind to my answer will raise your hand, okay? Before we actually do it. I'm going to tell you exactly how it'll work. Okay. All right, what's going to happen is the two balls come along here at the same speed. Now, when they get to this position, this ball, the ball on the front track, will go faster, won't it? So it'll get ahead, right? When it gets back up to here, this one will slow down. But of course, it's already gotten ahead. It's just slowing down to where it was, so it'll be ahead. And here, then, they'll be going along at the same speed with some small distance between them, and the ball on the dip track will get there first. Get here first. Everybody follow that? Who wants to change your mind? Raise your hand. Not very many. Okay, well, I guess we're just going to have to do it, right? Now let me do this again. In fact, it works exactly how I told you it works. The reason why I like this experiment is that I've done this for whole classes of physics students at the university, and they don't believe me either. I think this is probably the best example that I've ever seen of why you need to do physics experiments and demonstrations in a physics class. Otherwise, if you were in my class, I'd just have to tell you, and you could believe anything. Let's try it again. When the two balls go along at the same speed, they're together. When the front ball goes down, it goes faster, so it gets ahead. They slow down to the same speed here, but speed and position aren't the same, are they? It's gotten ahead by going faster in this distance, in that part. Therefore, the front ball gets ahead and stays ahead and wins the race. Okay. Here I've got two identical balloons. You can tell they're identical because they're both white. I'm going to blow up one about that way, and the other one blow up a little bigger. Is that about right? Yeah. Now, put that on the other end of the tube here. Of course, the air can't flow anywhere now because the clamp is in place. The question is, what's going to happen when I remove the clamp? Will the small one get smaller and blow up the big one? Will they become equal, or will they stay the way they are? What are the balloons going to do when I let the clamp off? They're thinking about it. I know. I can smell rubber burning. All right, let's vote. Who says when I release the clamp, the small balloon will get smaller and blow up the big one? Raise your hand. A few hardy souls. Good. How about they'll become equal? Good. More. How about they'll stay the way they are? Few there. All right, you ready? Of course, when I let the clamp off, gravity pulled the air down from the upper balloon. No, I guess it wasn't gravity after all. Let me answer the question as to why this happened by asking you another question. When is it hardest to blow up a balloon? Right at the beginning, isn't it? When the rubber membrane is thicker and therefore pushes back against your breath more, exerts more surface tension, isn't it? And therefore, there's more pressure in a small balloon, in the smaller balloon, than there is in a big one. And the smaller one will always blow up the bigger one. True for soap bubbles, too. If you can rig up a little gizmo with glass tubes and stopcocks and blow soap bubbles, you'll see that the small one always blows the big one up. All right, good. So we don't have too many more here. Let's see. You only have a few more chances to increase your score. Everybody knows, of course, that when you heat up something, it gets bigger. It expands, right? Hot things expand. For example, this metal plate, when I heat it up, will expand. The question is, what will happen to the hole? A circular hole in there. Will that hole get bigger, smaller, or stay the same size when I heat this plate up? See, to do the experiment, we're going to need to heat the plate, so we'll do that with this little gas burner. All right, are you ready to vote? Okay, who says when I heat this plate up, the hole will get bigger? Who says smaller? Good. How about stays the same size? All right, this is a good group because the real question here is what happens, how does this plate expand, isn't it? And a lot of you say the plate will expand, and therefore it should expand out and into the hole. Now, those of you who said the hole stays the same size, I think are wimps, aren't you? Because you aren't willing to go all the way with the idea that the brass expands. We're going to have to figure out how to measure this. Tell you what, could you feel that hole? Yeah, all right. The size of it, all right? With 2 fingers. You better do it 2 fingers. So yeah, okay. All right. Now I'm going to heat it up, and then after I heat it up, I'll let you. Maybe we better think of a different way. Let's use this ball, which doesn't quite fit into the hole. Let's do a little thought experiment while we're heating up the plate. Suppose that rather than having a hole there, I just had a scribe mark or a circle drawn with a pencil. A circle. Now, would that circle get bigger, smaller, or stay the same size? It'd get bigger, wouldn't it? Because after all, it is a piece of metal in there. Now, suppose that rather than a circle, I had a crack. So I could remove the little piece of circular metal before and after I heated it. Would the plug in the middle get bigger or smaller? Get bigger, wouldn't it? Because after all, it is a piece of metal. So the hole from which it came has to get bigger also. And it does. All right, we got one last experiment. Here's the question. When you look at yourself in a plain mirror, like a bathroom mirror or whatever, is your image inverted top to bottom, left to right, front to back, all of the above, or none of the above? Now, just to remind you what your image looks like in a plain mirror, I brought one along. Now, let's see. Maybe we better go ahead and vote here before we do any experiments. The question is, what happens to your image? Is your image inverted top to bottom, left to right, front to back, all of the above, or none of the above? You can vote for more than one here if they're all consistent. All right, let's go ahead and vote. Who says when you look at your image in a plain mirror, it's inverted top to bottom? Raise your hand. Yeah, this group pretty much knows which end is up. That's good. All right, how about left to right? Raise your hand. Inverted left to right. Okay, good. How about front to back? Raise your hand. How about all of the above? Raise your hand. How about none? Raise your hand. Okay, good. All right, let's see. X, Y, and Z. Red, white, and blue are X, Y, and Z. And I'm going to put the coordinate system on here in the normal way, X to the right, Y up, and Z to the bottom. And notice that it creates an image that back there. I need a victim here, a helper. Good, you make a good helper. Yeah. What's your name?
Tyrone.
Tyrone?
Yes.
Okay, Tyrone. I want you to take this. This is an identical frame of reference here, okay, Tyrone? And what I want you to do is to hold it above the mirror so that it's oriented the same as the reflection. Okay? Hold it above so that it looks the same as the reflection does. Help him out. He's having a problem. All right, let's do this, Tyrone. I happen to have another frame of reference here. This is the original one. And this other one has the X and Y in the same orientation, but the Z is in the opposite direction. All right, hold that one up like the reflection. Is that right? Stand back out of the way so these guys over here can see it in the cheap seats. All right, did he do it right? Yes. Okay, good. Now, Tyrone, you stay there for a minute. So what Tyrone has established here is that, in fact, there is one inversion in a plane mirror, isn't there? One of the three axes is inverted. So now we got to figure out which one. Let's see. We'll use you as the victim here. All right, come on over here. Look at yourself in the mirror, Tyrone. You're a little cut off here, but that's all right. You can imagine. Oh, yeah, just sit down there. All right. Now, if when Tyrone is here in the flesh, let's see, his head is pointed that way. Let's not worry about left and right and up and down. His head is pointed that way, and his feet are pointed that way. How about in the mirror? His head pointed what? That way? And his feet are pointed that way. So there's no inversion, right? Okay, Tyrone, hold your left arm out and wiggle it a little bit there. Now, Tyrone's arm that's pointed off in that direction is wiggling, right? In the flesh here, right? Right? Yeah. How about in the mirror? It's the one that's pointed off in that direction. So, son of a gun, there's no, go on over. There's no inversion in that direction either, is there? Because Tyrone and his image are both pointed in the same direction now. Now, let's do another experiment. All right, Tyrone, up. Good lad. Let's see. Suppose I'm going to be the object here, and I'm standing in front of it. Now, Tyrone, I want you to go stand over there like my image. Did he do it right? What did he have to do? He had to turn around, didn't he? In fact, a plane mirror inverts your image front to back. If it didn't, what would you see when you looked in a mirror? Your back, right? How many of you see your back when you look in a mirror? Not very many. So, a plane mirror inverts your image front to back, not top to bottom, not left to right. I guess the most important thing about this is how you actually define what an inversion means, isn't it? Thank you, Tyrone. Good job. Let's see. In the physics literature, this is known as a perverted image. Seriously, it really is. If you look at the literature where they talk about this kind of a reflection, this kind of an image, it's called a perverted image. Well, that's all we have time for. I do want to talk with a few of you about your scores. Actually, I hope that you all don't feel like the ornithology student. Everybody know what ornithology is? Study of birds, right? This student, he was in a graduate course in ornithology. He already had his bachelor's degree, and he was working on a PhD. And it was a large class, about 200 students or so, in a very large lecture hall, much larger than this. And it was the final exam time, and they all came into the lecture hall, spread out the alternate rows, 3 seats apart, the honor system, and ready for their exams. And the professor came in, and he had 200 tiny little shoe boxes, these baby shoe boxes. And in each one of the shoe boxes was a little bird. And in the bottom of the shoe box were 2 little holes. And the bird's feet stuck out through the 2 little holes in the bottom of the box. What was the final exam? Guess the bird, right? You had to guess the bird by the feet sticking out through the bottom of the box. Well, everybody got one of their boxes, and they were all examining their feet and shaking their box to see if they could identify their bird. One student became very upset, stormed down to the front of the lecture hall, slammed his box on the lecture table, said, "Professor, this has got to be the worst final exam that I've ever had in my graduate school career." The professor was sort of shocked by this, didn't know what to say, a little tongue-tied, and sort of stammered around a little bit. That gave the student a little more courage. He says, "In fact, your course in ornithology is about the worst course that I've ever had in my college career." And that even shocked the professor more. I mean, he's starting to sweat, face get red and all this. And that didn't say anything, still tongue-tied. That gave the student more courage. He looks the professor in the eyes and he says, "In fact, you have got to be the worst teacher that I have ever had in my life." And the professor now, he was really upset and sweating, and finally he regained his composure. Looked the student in the eye and said, "Young man, what's your name?" I said, "Guess." Well, hope you enjoyed the physics IQ test. Thank you.
Thank you very much. I thought that was really good. For anybody who'd like to ask Vic first some questions, come on down and we will have you.
We need to go to sleep. Where's your dad? Thomas, thank you. Juliette is going to Let go, Thomas. He's going to sleep.